Okay, guys, so we are now to understand the important things we need to know about linear elasticity. So, two-dimensional in that. So, we have actually two types of problems that we might encounter when we refer to two-dimensional linear elasticity. One is the plane stress problem, and the other one is the plane strain problem. Okay, for the plane stress problem, this is defined as the type upon which the geometry of the body is essentially that of a plate, no? So we're referring to any material, may it be a steel plate, a timber plate, aluminum plate, a concrete plate, okay? Wherein one of its dimension is very small compared to the other dimension. So the thickness, to be uh, much clearer, is actually small compared to the dimensions defined on the geometry of the body itself. So we are now going to imagine those plates, the steel plates with a very small thickness, let's say 1 inch, and then the dimension is maybe 2 by 4 meters. So it actually falls within the scope of the plane stress problem. But that is not just the definition of a plane stress problem. If you want to use the concepts presented here, the other restriction is that the load, okay, must be applied uniformly over the thickness. So if you have a thickness, let's say T here, so the load must actually be uniformly placed, no, on the thickness, and that's not very hard to achieve because of the thickness, because of the comparison of the thickness with the other dimensions. Then when you apply a load, okay, parallel to the plane of the member itself, then it is quite achievable to allow, no, the load to be uniformly distributed throughout the thickness of the plate. And it should of course act on the plane of the plate. If along the plane of the plate, if the plane of the plate is actually defined on the basis of the plane of the bigger dimensions, then uh, this force here, which is assumed to be distributed, acts along the plane of the plate. In terms of functional requirement, uh, mathematical criteria, we now define a a plane stress problem in this regard. Okay, so the stress is a function of the plane upon which the load is acting along. Okay, so if this is the x1, x2 plane, which is defined by the orientation of this plate element, which is arbitrarily bounded, no, then I can say that this is a plane stress problem. So, ito yung mathematical definition. Yung kanina, yung dinescribe ko sa inyo is a more of a geometrical definition. So, for the field equation, you will notice that sabi ko kanina, ano yung component natin sa, ano yung criteria natin sa structural analysis. Always, class, when we refer to structural behavior, we simply define these field equations. These field equations was proven to be derived from the motion field and therefore defined in such, ito lang yung tinatawag nating equilibrium equation, or this is the summation forces equals zero. Ito yung tinatawag na generalized Hooke's law or the constitutive equation. Okay? At ito yung tinatawag nating strain displacement relation. So, where's the compatibility equation? Sabi ko nga, yung compatibility equation is just a restriction to check later if you have some doubts on the compatibility of the motion of the particles inside the body in terms of displacement, then you have to check it. Okay? So, ito yung field equations natin. And this field equations is a tensorial equation. It is not a one a scalar or a zero rank equation. Rather, it is actually a second order tensor in that regard if you are considering it in 2 or 3 dimensions. So, ito ngayon yung ating stress tensor, and this is the strain tensor. Okay, so notice, sigma is only a function of 2. Automatically, you don't have any value, no, on the third axis. Okay, but the strain has what? A displacement or a strain value on the perpendicular axis, on the axis perpendicular to the plane upon which your sigma is defined, and that is your 3-3 axis. Okay, so this is brought about by what? Sir, wala naman tayong force pero meron tayong strain. Bakit? This is actually carried by the law of or the principle of lateral displacement as proven by Poisson. No? So you have a Poisson's ratio that contributes to the lateral strain, okay, reckoned from the plane of loading. Okay? So, ito yung wag nating kalilimutan din. Not because this is a plane stress problem, then we ignore the longitudinal component of your strain perpendicular to the plane of loading. Okay? So, for the plane strain problem, the displacement component U3 is the one that is defined and taken to be zero. Okay, dito ano yung define natin? Sigma, stress. Plane stress, meaning to say, you don't have any stress on the third axis. Plane strain, meaning to say, you don't have a displacement on the third axis, or it can be thought of as the strain on the third axis is negligible. Okay, so this is now the mathematical definition of a plane strain problem. But if you look at the geometric description, you are now considering a very long So the length here, or if we call it the width, okay, so we can term it as the width, is actually very big compared to the geometry upon which your plane x1, x2 is referred. Dito baligtad, no? The thickness is small compared to the boundary, the geometry upon which x1 and x2 is reckoned, no? Here, the thickness is very large, or the width is very large compared to this boundary. Okay, so it's the other way around. That's why it's called the plane strain problem, because your definition for the motion field, which is the displacement at the third axis, is 0. Okay, so it's plane strain. Wala tayong third dimension. 2 by 2 lang. It's plane stress because we don't have a third dimension sa 2 by 2 stress. Okay? Okay. Take note. It doesn't mean that since your strain is 0 there, you don't have a sigma 3. You may or may not, what? Consider sigma 3. Why did I say you may or may not? Because if there is no strain here, or you have a very small strain here because of the large dimension, the particle cannot move, okay, in this direction, then sigma 3 sometimes may be insignificant. But not all the time. Okay, that's why normally when you have a plane strain problem, sometimes they ignore the stress at the third axis. So let's say you are designing a dam, okay, a very long dam or large dam, okay, wherein the width is very big compared to the geometry of the dam. Normally, you don't also require a check on sigma 3 because the strain is assumed to be negligible or 0. But it doesn't mean that there's no sigma 3 because the definition of the plane strain problem does not say so. It says that only the displacement field is defined on the basis of the plane of loading geometry. Okay, so if you are talking of the x1, x2 as your plane of loading, then uh, your third axis x3 is the one that is negligible in terms of strain. Okay, so again, you have three field equations, the equilibrium equation, the constitutive equations, or what you call the generalized Hooke's law, and the strain displacement relation. So take a look on the uh, Hooke's law, or the generalized Hooke's equation or constitutive equation. They are differently expressed, but they are just the reciprocal of the other. Meaning to say, if I inverse this and substitute the modulus of elasticity and the Poisson's ratio in terms of the Lemay constant lambda here, then, and mu, then I can get the same. Okay, so just look on the other references, but I'd just like to inform you that this is just the inverse of each other. Here you are solving for the strain, here you are solving for the stress. So why did it, bakit ganito ang ginamit? Kasi ang kailangan mong malaman dito is yung strain because given yung stress field mo. Dito naman, ang kailangan mong kunin yung stress kasi given yung displacement or strain field mo. Given yung displacement. So that's just the reason why they are expressed differently in these two problems. Okay, so do you have any question on on that, or maybe we can continue first, then we address your concerns later. Okay, so let's move on to some of the useful um, tool for us to be able to solve uh, plane elasticity problems or plane elastostatic problems. So let's have some understanding on the Airy stress function and how it was used, no, to solve some problems on plane elasticity. Okay, so this Airy stress function is simply very similar to the stress surface that Cauchy, okay, has proposed. This is not a vector; it is a function wherein the stress field is converted in a form of a surface equation. Okay, it's a surface function. It's a stress function uh, that was used to simplify the formulation of a stress solutions in two-dimensional elasticity problems. So recall the equilibrium equation with no body force. So there's no body force here, meaning to say the self-weight, the inertia force are not considered. We also take a look at the compatibility equation for plane elasticity. So here it is in the form of the Eulerian, so E. So for a plane elasticity problem, we may um, get these two equations here from equation 1. Okay, so if I want to expand this, this is a what? How many equations do I have? So this is a first order equation. So I actually have uh, two equations because we are on the plane elasticity. We only have two axes. So 2 to the 0 is okay. So 2 to the 1 is two equations. Okay, so we have a first order equation. Why? Because you have only one index. Okay, so kailangan perfect yun na to. Ano? Kasi pag nagbasa kayo, yung mabilis yung understanding. No? Bago kayo antukin, meron na kayong naintindihan. So, yun ang hirap sa mga babasahin natin yan sa engineering. Lalo na pag nasa level na kayo ng master's degree. Nakakaantok ng basahin yung mga libro, yung mga literatures. Okay, so ito, madali pa. So we have only kaya you expect here two equations. Okay, so this can be in this form, comma. So this is simply the partial derivative of sigma 1, 1 with respect to x1. Again, I'm using an Eulerian form. That's why I use a small letter there. Okay, and eventually you will notice that since Eulerian is more descriptive on the final position of your particle instantaneously. That's why they use always Eulerian, no? Eulerian na yung ginagamit. Okay, so this is now the partial derivative of 2, 1, okay, 2, 1 with respect to x1 plus partial derivative 2, 2 with respect to x2. So these are just equivalent, no? Parehas lang ito, no? Okay. So for equation 1 and 2 to be satisfied, the only hope is to equate them. Okay, so this and this, if I transfer the other on the left hand side, I will get this one. So my only hope is to make a dummy variable that would make this equal. Okay, for them to be equal, I will insert a dummy variable. Let's say if I let my sigma 1 1 as the partial derivative of f with respect to x2, and sigma 1 2 as the negative partial derivative of f with respect to x1, then I will come up with an equality. Tama? I will come up with an equality. So I'm just forcing the issue now. I'm using a method to force the issue, to force this to be equal, or else I cannot move on to my objective. And on the other hand, looking into this second equation here, okay, if I take the partial derivative of, if I take sigma 2 1 as the negative partial derivative of g with respect to x2, and I take sigma 2 2 as the partial derivative of g with respect to x1, then I force this equation to be equivalent, or these two values to be obviously equal. Okay. Now, on the third hand, I now make use of another assumption. In this case, I want to make g and f somehow a function of phi for me to be able to simplify things out. Okay? And make a more um, useful equation, useful expression, no? to use on two-dimensional elasticity problems. So if I take the partial derivative of, or if I take f as the partial derivative of a function, which you are now actually, so this is now the area function. It's a stress function because the stresses are involved here, okay? Okay, so and substitute it later on the value here, so I will get this one here. Okay, so I will now get sigma 1 1, a double partial derivative of phi with respect to x2, and sigma 2 2 as a double partial derivative of phi with respect to x1. And of course, my sigma 1 2 will be a partial derivative of phi with respect to x1 and x2, and just forget the other, so which are just the same, no? So nagbaligtad lang ito, x2, x1, something like this. Okay, so I have now a function defined by this, which I can conveniently use to form another function, which is called the biharmonic function. Okay, when you say biharmonic, if you try to recall your advanced mathematics, I don't know if you have studied. So this is a harmonic function. Okay, when you simplify a harmonic function, you actually take a look at the sinusoidal harmony, no? A sine wave, or maybe a combination of a cosine wave. So normally you use this very much on a Fourier series expansion, or a Fourier integral series, and so on. Okay, or transform, no? So this is a harmonic. So if we say biharmonic So you just use a del squared term there to make a biharmonic del to the fourth phi. Okay, so I did not place it here, but you just try doing it by simply substituting, okay, this sigma 1 1 in your original equation. Okay, so these are the two original equation coming from equilibrium equation, and then making use of elimination or substitution by addition and subtraction, you can get this one here, this one, which is the shortcut of what this biharmonic function is all about. Okay, so what does this mean? So this simply means that you are taking the partial derivative of phi with respect to, so if that is p11, so you have an x1, okay? Okay, something like that. Then plus the partial derivative of phi all over, okay, with respect, I mean. And then this is equal to 2 times the partial derivative of phi with respect to x1 squared, and this is x2 squared, something like this. So this is simply a symbolic representation of these partial derivatives here, where the symbol comma x denotes that the partial derivative of phi with respect to the subscript indicated in the trail. Okay, so if the trail is 1, 1, 1, 1, so these are all x1s. And if this is a 2, 2, 2, 2, these are all x2s. If this is a 1, 1, 2, 2, it's an x1, x1, x2, x2. Okay, so let's try to have an example here. For this problem, we determine the necessary relationship between the constants a and b. Okay, so this is just a mathematical exercise actually. It has nothing to do with the practical application of the area stress function on the solution to stress strain problems. So we are given an area stress function here, actually phi, that will satisfy our biharmonic function as derived using the procedure above. Okay, so what we are just getting here is the value of the constants a and b. So first we differentiate. We need to get the phi comma 1 1 1 1. Okay, so how do we do this? We differentiate with respect to x1 4 times. So the first differentiation, phi prime, okay, or yes, we can call it phi prime here because we only have to differentiate it with 1 1 1, or on the left. Gawin na natin phi comma 1. Okay, let's have it phi comma 1. So is equal to simply ito 0 na to, no? Kasi sa 1 tayo nag-differentiate. So this becomes 2a x1 x2 cube. Okay? Tama? Constant 2a.
Yes, sir.
Okay. So if I make a phi comma 1 1, it's 2a x2 cube. Tama? And then a phi comma 1 1 1 1, it's 0. Hindi ka man nakarating doon sa 1111, 0 na siya. So, 0 ito. Ha? Okay, let's go to phi 222. So, it's a phi, comma 2. So, if I make use of this first, I have now my 3. Okay, 3 times a x1 squared x2 squared plus 5b x2 to the fourth. Tama ba? Okay, so pakicheck
Yes, yes.
lang. Ako, dito na ako mahina ngayon eh. Sa mga ganitong okay, 2, 2. So this is 2 times 3 is 6a x1 squared x2 plus 20 bx2 cubed. Tama? Okay, so sabihin nyo kung may error ha. 2, 2, 2. Okay, so this is now, mawawala na yung x2 doon, magiging na lang 6a x1 squared plus 60 bx2 squared. And the last, p222 is equal to 0 plus 120 bx2. Okay, so tumama naman eh. Okay? So, how about a 2 phi 1, 1, 2, 2? Okay, let's have here a 2 phi, comma 1. Okay, yung 2 phi, comma 1, ito yon, di ba? Tama ba ako? So, mumultiply mo lang ito ng 2. Tama? So, this becomes 2 times 2 is 4. So, this becomes 4ax1 x2 cube. So, isa pang 2. Huwag muna kaya nating lagay yung 2 para hindi tayo mahirapan. Mamaya na lang. Okay, so this is 2ax1. Yeah. So, yung phi, comma 1, 1, comma yun, no? Is 6. Paano ba yan? Tama? Is 2. 1 pala tayo. So, 2. Ito yun, di ba? So, 2ax2 cube. Ayan. Ngayon, mag-iiba na siya doon sa phi, comma 1, 1, 2. Ayan. So, 1, 1, 2, magiging na siyang 6ax2 squared. Tsaka phi, comma 1, 1, 2, 2. So, magiging na siyang 12ax2. Okay. So, yung times 2 nito, magiging 24. No? So, 2 phi, comma 1, 1, 2, 2 is 24ax2. So, ito yun. Okay, so nakuha mo to, i-equate mo ngayon dito. No? So, it will become simply 0 plus 120bx2. So, magiging 120bx2 equals 24A AX2. Okay. So, cancel yung X2. Yung A mo ngayon is simply 120 over 24B. Negative ba? Bakit negative? Oh. So, may mali dito sa ating derivation. Okay. So, pag sinubstitute mo ito mamaya dito, magkakaroon ka ng negative. So, I think plus this is a negative sign. So, I'll be looking into this now. So, there's a negative sign. Okay? Kasi lilipat siya nasa right hand side. Wala zero ito no? Pag in-add mo yan, magkakaroon ka ng 2 dun sa 1, 2, 2, 1. Pag nilipat mo sa kabila, negative. Okay, the biharmonic del 4 phi class, if I am not mistaken as far as I want to remember it, is merong error lang sa lecture. Plus 2 phi, yan yung mas 1122 plus phi, comma 2222. Yan. Ito yung biharmonic formula. Okay? So, ito negative. Negative dapat. Pag nilipat ko, ito sa kabila. Okay. So, please take note on this. So, ito negative sign. Yan. So, my answer here is 120. 12 is 0.5. So, 5 siya. So, this is A is negative 5. Okay, so that is your final answer. So, any question? So, let's stop up to this point to address your concerns.